Beautiful. All right. Well, happy Science Week, everyone. Welcome and good morning, and welcome to stages 3 and 6 to our 3 to 6 to our virtual panel Q&A session that we're running in conjunction with National Science Week. Today, we're going to take a closer look at solar energy and find out how solar fits into the big picture for renewables and Snowy Hydro's energy mix. So we'll find out how renewables work together to power the national electricity market, and find out a bit more about our panelists, their STEM careers, and how they got to working in renewable energy at Snowy Hydro. Last time we ran the virtual panel, we received so many terrific, hard-hitting questions about renewable energy from you, and we can really see it's a subject area of focus. That will again feature in today's session, and we'll go into looking in the lens of contractable renewables at Snowy Hydro. Don't worry, we'll explain that. And understanding our energy mix. Our panel of engineers will answer your questions, and together we'll learn more about solar, the renewable energy mix, and the NEM, or the National Electricity Market. You would see on the top of your screen that this is being recorded, and it will be uploaded to the Next Generation Online Learning portal on our website, so you can have access and watch it again. So getting into it, just want to say a quick shout out to a couple of the schools we know we have here. So we've got the Snowy Mountains Christian School, Cooma North, and Tumbarumba Public School. So welcome there, and I'm sure there's a couple others that I'll see as we're going through. Before we get right into it, I'd like to perform an acknowledgement of country. So we would like to acknowledge the tradition custodians of the land. For me, the Minderibba people on which I meet from you today, and all the various lands where you all are, because we're all separated, and pay respects to the elders past and present. We're all on different lands today, and so acknowledge those who have come before us. So, without further ado, we'll get into it. My name's Kush, and I'm going to be your host for today. But today we're going to get our fantastic engineers here to look further into the theme for this year's National Science Week theme. So that's glass more than meets the eye, and we'll find out some pretty interesting ways how that fits into renewable energy. Learn more about Snowy Hydro's role in the renewable energy sector. Investigate solar energy and how it fits in with the mix, and learn lots about STEM career pathways, and learn a bit more about our engineers. So without going too much further, I'd like to say hello to all our panelists. We've got Varden, Beck, and Jed here today, and they'll take you through, I suppose, all the big questions and themes of this panel. But I might let them introduce themselves. So can you tell us, guys, your name, where you came from, what you do at Snowy, what team you're part of, and a little bit about how you got here. Might throw to you first, Beck.
Yeah, thanks, Kush. Hi, everyone. My name's Beck. I'm a graduate mechanical engineer, and I'm currently in the Murray region, which is out near Cancoban. And that's actually the background I've got. That's Murray 2 power station there. So, so if you're ever out that way, it's pretty cool. Pretty cool view. I'm on a grad rotation, so we move around to different teams every 6 months. So I've been in this team for about a month now. Before joining Snowy, I studied at Sydney University. I did mechanical engineering and project management. So that's a bit about me, and I'll pass on to Jed.
Yep, good morning, guys. My name's Jed. I'm originally from Albury, just a couple hours west of where I am today in Cooma. I'm a graduate mechanical engineer as well. I did my degree at the University of Wollongong, which was a nice couple of years at the coast. And so currently I work from our main office here in Cooma, and this is my first year at Snowy Hydro. Would you like to tell us a bit about yourself, Varden?
Yeah, go guys. My name's Varden. I'm a site engineer out at Cancoban, just up the road from Beck. I've been at Snowy for just under 3 years now. Originally, I'm from the Central Coast, so just north of Sydney, up near where Kush is at the moment. And I studied I studied engineering at the University of Newcastle. So it's taken a little while to get used to the colour down here, but I'm getting there slowly. Keen to share some things with you today.
Awesome. Thanks, guys. My name's Kush. I also studied mechanical engineering, but at the University of Western Australia over in Perth. So came across the desert probably last year, started at the same time as Beck, actually at the same graduate cohort. So I've been here for over a year and a half, and currently I'm working up in the Hunter on the Hunter Power Project. Just super excited to be here and really have enjoyed all the opportunities that I've been able to get in the Snowy Mountains with Snowy Hydro and now up in the Hunter. So keen to get into it. Before we go a bit further, though, understanding a bit more about your teams, guys. Obviously, you're all in different roles, but we're all one company. And Varden and Beck, you're pretty close together. You're both in the Murray region, except doing different roles. Can you do your teams work together? Can you tell us a bit about how that sort of works together?
Yeah, definitely. So I'm in what's called the production team. So we're looking after both Murray 1 and Murray 2 power station and kind of looking at the day-to-day maintenance and running of the plant. And Varden works in the major overhaul team. So they're more project focused and based at Murray 1. So we do work quite closely together because sometimes similar issues crop up. So we might work on the problems together and sort of share our ideas. So it's really good to have knowledge from other people as well.
Yeah, definitely. And working in the major overhauls team, the production team that Beck works in, really, they know the machines just about better than anyone else. So, we're here rebuilding them, but they know how they operate. So it's there's definitely a lot of communication across teams, and we like to seek their advice when we can. And because at the end of the day, once we rebuild the machines, it's going back to Beck, and we don't want to give them back a machine that's going to break down. So
I can imagine, and it's pretty cool to see that you guys are moving through and working together, and there's a lot of collaboration. So Jed, you're in asset engineering, so that's not necessarily based in a region, but I take it you work with all the regions. Can you tell us a bit about what you do, what your team does, and how that works together, for example, with these guys out at Murray region?
Yeah, absolutely. So in asset engineering, our role is to ensure the health and integrity of our assets. So that's things like looking at reports that might be generated by production or major overhauls teams. We also take time to go out to our different assets and have a look at them. So we're looking for signs of wear and tear on the machines, such as cracks, corrosion, which is a fancy word for rusting, and other things like that. And then what we do is we try to make a picture of what state we think that asset is in and how much longer it has left before we have to do something to it. And if we identify big problems, we want to come up with a solution to fix that problem to prolong the life of our assets. So, as I say, we work quite closely with other areas of the business, particularly production and major overhauls, as they can carry out some of the bigger things we think need changing. And as we mentioned earlier, we get to go to many different places around the scheme. So our knowledge base might not be as deep and as detailed as people in production or major overhauls, but we sort of deal with everything around the scheme. So we've got quite a lot of exposure.
Sounds like a pretty interesting role. You get exposed to a lot of different things. So I suppose pretty exciting and keeps it interesting.
Yeah, absolutely, mate. It's awesome.
Awesome. Well, it sounds like you guys have got a pretty wide range of experience and cover a fair bit of the business. So I suppose there'd probably be no better group to ask about Snowy Hydro. So we'll kick into some of the questions, and we'll start off at the top level, and just learn a bit more about how Snowy Hydro underpins a transition to a renewable energy future. So what does that mean and we'll find out what that means in the context of the renewable energy mix. So Beck, can you please just tell us what role does Snowy Hydro play in the renewable energy sector?
Yeah, definitely. So just to start off though, I'll just define what renewable energy is. So it's any electricity that's generated from a renewable resource. So that means that the resource is like naturally replenished and it won't run out. So this could be like solar energy from the sun or wind and water as well. So Snowy Hydro plays quite an important role in the renewable energy sector. So you've probably heard about or maybe even seen some of our hydropower stations, which are scattered around the Snowy Mountains, and one of them being Murray 2 behind me. So we use these power stations to generate electricity by using water, which is a renewable resource. And then we can use that electricity and we send it to homes and businesses all around New South Wales and Victoria. So yeah, it's quite an important role there. But in addition to this, we also have agreements with some solar and wind farms, so we can buy renewable energy without actually having to own the equipment. So yeah, we play quite an important role.
Yeah, right. Sounds like there's a pretty integral role there, and we're sort of all over the energy market. Now, you did mention, and this I'm a bit unclear about, so I might get you to clear it up for me. We have wind or solar or agreements with them. Generally our assets are predominantly hydro generation. So what are we talking about when we say, wind and solar renewable energy contracts with Snowy Hydro?
Yeah, so we don't actually own wind or solar farms ourselves. So we're not putting the money in to build them and run them ourselves, but we can sign agreements with companies who do own them, which kind of gives us access to their renewable energy. So the renewable energy contract is it's kind of an agreement between two companies, and they agree to supply a certain amount of renewable energy. So to sort of put it in a bit of a simpler term, I'll just say, let's say I had a company, I'm going to call it Beck's company, and I want to buy some renewable energy. And so I might go to an energy provider who might be Kush. So Kush has some solar panels in his backyard, and he's selling renewable energy. So I'll go to Kush and I'll say, hey, can we make an agreement? Can we sign a contract? I'll agree to purchase a certain amount from you if you agree to provide that energy to me. And the benefit is I've sort of guaranteed, so Kush knows that there's going to be some money coming in, so then he can use that money to go and build some new solar panels or wind farms, and I can guarantee that I'm going to get the renewable energy, which I might use to power my office buildings or charge my electric vehicles, or I can use it in any way I like, but I'll know that the energy is clean. So
very nice.
Yeah.
So we can make an agreement for you to basically buy all the electricity that I'm generating, so I know it's being used and I'm going to get paid for it.
Exactly. Yeah. So you guaranteed that you're going to have money coming in, so then you feel confident to go and invest in some new infrastructure and purchase some new assets. So yeah, so that's pretty much what happens with Snowy Hydro. We have contracts called power purchase agreements, or PPAs. So it allows us to buy solar or wind energy without actually having to own the asset, because it is quite expensive to get solar and wind farms up and running. There's a lot of equipment to buy and install, and it takes a lot of time. So it can be difficult for companies to get things up and going. So Snowy Hydro commits to buying a certain amount of energy at an agreed price. And the benefit for Snowy is that we've got a locked in price and we have access to this energy, and then the company has the benefit of knowing the money's coming in. And I guess the benefit for everyone is that most of these projects are done in regional Australia, so there's a lot of jobs created for local people. Yeah.
Awesome. All right. So yeah, it sounds like it's a pretty vast range then of energies that are in our mix. We've got solar and wind that we're partnering with, and then have our own generation assets. If we're going to dive a little bit deeper into solar energy and the theme of the whole National Science Week. We'll jump into it. So, Varden, how do solar cells or photovoltaic cells actually make energy? So, how does solar power work?
So that's a pretty good question, Kush. And to be honest, I needed to do my homework on this one because I'm definitely no expert. But to kind of give you an idea of how far we've come in this space, I'll kick off with the first solar panel invented was in 1954, or successful solar panel was in 1954, and it had an efficiency of 5%. So that meant for how much energy you put in, you only got 5% of it out. So that's a pretty small portion. And now the world record for this is up around 47.1%. While that's in a laboratory and you can't replicate that out in the field or on your rooftop, that's still an impressive feat. So that's over a 9 times increase in the amount of power we can get out from a panel. So, we've come a long way, but I think from the way things are going, we've got a long way to go. So, but solar cells rely on what's known as the photovoltaic effect. To kind of simplify that basically means it's a way of converting sunlight into electricity. And the main material used here is called silicon. Now, it's used a lot in computers and microchips, and in particularly, we do what's called doping silicon. So basically, if anyone's played with magnets before, you've got a north and a south end of a magnet. And so that's really a positive and a negative charge. And that's all to do with the electrons in the atoms. So we won't dive into that because that's a bit boring. But so basically what we do with the doped silicon is we make a north and a south magnet. So we put these two materials together, and what we can do by adding slightly different materials into the silicon, that's how we get the north and the south. And we can then, these are called P-type and N-type materials, by the way, but that's diving a bit too deep. But what we can do is that if these certain types of materials, we expose them to sunlight, and the sunlight gives them a kind of kick in energy, which then allows the negative charge, or the electrons in there, to flow through the material. And that's kind of that changes where your north and south poles are in that material. And then how this becomes useful for us is we expose these materials to sunlight, and then we connect a wire to each end of it, and then we get these electrons to flow through it. And so, that's important for us because we get these electrons to power the things we use, whether it be the lights in everyone's classrooms or your laptop or your microwave at home. So that's that's a very simplified version. If anyone wants to dive deeper, I recommend speaking to your local science teacher or looking up on YouTube. That's kind of how we are.
If I'm recapping and trying to understand correctly, essentially the sunlight, so light energy, provides the energy to move an electron through this material, so it's dislodged from where it's sitting dormant without sort of being excited, and then because that electron is released or is able to move, and we're able to capture that movement into a wire and like downstream in our circuitry, then we can use it to generate. Is that correct? That's essentially correct, and it's quite a complicated process. That's why there's still people working in laboratories away on this, trying to improve it. But that's a simplified version of what's going on, and as I said, refer to your local science teacher for a better explanation. Awesome. So can you tell us then a bit more about, how, like with that basic concept, how have we designed all the, the big solar farms that we have that you see driving on highways, and then everyone's solar panels directed in a certain way on roofs. How does that work?
Yeah, so these solar farms, there's actually a bit of work that goes into the design of them. They're not just, someone doesn't just rock up and just drop some panels in a field and then drive off, There's a bit more work into it. And, in Australia, you might notice if you see a few different solar farms close to each other that they're all facing the same way, and they're facing north. And that's generally because, on average, the position of the sun is at the equator. So, we position our panels north to try and capture that average position of the sun. But what this kind of means is, like, if you live somewhere else in the world, say if you lived on the equator, you'd want your solar panels to be flat because on average, the sun is right above you. But then if you lived at the South or North Pole, you'd want your solar panels to be facing vertically. Standing up vertically. So, yeah, there's kind of a bit of science goes into this, but it depends on where you live. And another way that we like to kind of capture the most of the sun is that we vary the way the panels face from east to west. So everyone knows that, the sun rises in a different spot to its sets. So it rises in the east and sets in the west. So a lot of our solar panels can actually, especially on the solar farms, actually follow the sun from east to west. So in the morning, the panels will be on these, they're all on these motorized stands. And in the morning, they face the east to catch that morning sun. And then as the day goes on, they follow it to be directly overhead. And then in the afternoon, they follow it to the west to capture that afternoon sun. So not every solar farm would be doing that because, that's expensive and it depends on how much people want to invest in the solar farm. But yeah, that's a pretty common one. And but some more simple designs they're based off the surrounding geography. So, the bush or the mountains around the solar farm. So if you've got a big range of mountains in the east of the solar farm, you might try and just capture what's going on in the west. So you get that stronger afternoon sun as opposed to the morning sun. And it kind of depends on the market demands as well in the local area. So, in the afternoon, if you were like me when I came home from school as a kid, I ate everything that I possibly could. So I was using the toaster, the microwave and the kettle all at the same time. So you might want to capture that afternoon sun to cater for that demand when people come home and start cooking food. So, and likewise, you might try and capture that morning sun to generate electricity when people are cooking their breakfast in the morning. So, yeah, there's a bit that go into them. And, it can be as simple or as complex as you make it, really.
Beautiful. Well, I now know that when I drive on the highway and see these solar farms, I'll be hopefully in the passenger seat and can look which way they're directed. Are they directed north or are they directed west? Do they have something that's tracking the sun? It's going to be pretty interesting to see. And I've got some solar panels at home in Perth, so I might go check and get a compass out and see which way they're pointing. So it'll be pretty cool. You've given me a bit of homework to do. So thank you heaps for that. Now, Jed, I'm gonna go out on a limb here and say you're a bit of a solar guru, solar expert, because you did your thesis on something pretty interesting in the space. But before we get to talking about that, the theme is glass more than meets the eye. Can you tell us a bit about how glass fits into the design of solar panels and what sort of things you're looking out for when you're designing them?
Yeah, no worries, Kush. I'd say that I'm pretty far from an expert, but thank you for the compliment anyway. So, as we know, the theme of Science Week is glass more than meets the eye. So, when we think about glass, everyone knows what it is. It's see-through, it's hard. If you try to walk through a glass door without opening it, it's going to really hurt. But when it comes to designing solar panels, there is actually some different things you want from your glass. So the main three things that we think about are what's called transmissivity, which is how much energy can pass through the glass, absorptivity, which is how much energy is absorbed by the glass as your light passes through, and reflectivity, which is how much energy or light is just going to bounce straight off the glass, and the glass wants nothing to do with this light. So you'll notice that all solar panels have a layer of glass over the top, and that's generally just to protect them from getting dust on the collectors, which is the black parts, which is the silicon that Varden was talking about. In this case, we want a glass that has high transmissivity, so that as much energy as possible can get through that glass and to the collector. Low reflectivity, so that none of the light is bounced off, because we don't want the light to bounce off. We want to get all that light into the collector. And low absorptivity, because you don't want any of that energy or heat to be absorbed by the glass, because then that's less that's getting through to your actual panel. So you can get these different qualities by putting different elements into your glass. An element is just what the world is made up of, essentially. So yeah, that is where glass comes into conventional solar panels.
Mm-hmm.
But there are different forms of solar energy. So I completed my thesis, which is essentially just a year-long report, which I ended up writing 90 pages about this, on what's called solar thermal energy. So as some of you might know, thermal means heat. So what that is instead of generating electricity from sunlight, you're using specially shaped mirrors to focus that light to a central point. And I did this in the context of making drinkable water from seawater. So I also looked at some things called solar stills, which is another thing where you want that those different properties in your glass.
Sorry, you go.
No, you go, Kush.
Well, so how like, what would you have to change about the glass to use it for solar thermal as opposed to, the conventional solar panels? Like, how's that different?
Yeah, absolutely. So in the case of a solar thermal plant, you want mirrors. So again, you want that high transmissivity and low absorptivity, but you also want a bit of reflectivity, because what you're wanting is for the light to reflect off your mirror and then to a central point. So that's how you get the heat. I worked with things called trough collectors, which is, if anyone knows what a parabola is a parabolic shaped mirror which focuses your light onto a central axis where you have a working fluid.
Right.
And that's used to heat water. A really cool application of this that they've got a few of over in America in their hot states like Nevada and California is what's known as a heliocentric field. But I call them power towers because that sounds way cooler. So what that is a large area of land that gets a lot of sunlight, and all around this land are mirrors that are all positioned so that when the light shines on them, that light's reflected to a central point in the field. And at that point, you've got a massive tower with a lot of water in it. And that gets really hot. I think off the top of my head, something like 600 degrees Celsius. So that water boils and turns into steam, and then the steam pushes a turbine around, which makes your electricity. So that is some of the different ways that you can use solar power and glass to make renewable energy.
Yeah, wow. That's really awesome. So is that also then the way that, the other things on the roof, solar hot water works?
Sort of. So again, as some of our students might know, you want to increase your absorptivity for an application like this. And the easiest way to do that is just paint it black. Anyone who's really into like Metallica or something who's gone out in summer in a black band t-shirt, you'll know how hot that black things can get. So for solar hot water, you essentially have these channels or pipes of water that are painted black, which raises, as I say, the absorptivity of the material. So then as energy comes in, it's absorbed by the cover gets hot. Because the water's in the water gets hot, and that's how your solar hot water works.
Right. Yeah. Okay. Cool. I get you. Well, that's awesome. That's a few different ways that I didn't know that glass was used with solar energy, literally just in different forms and different applications, it seems. So, sometimes we have it on our roofs and in farms to generate electricity. Sometimes we're heating water to generate electricity with, a more conventional turbine generator. And then sometimes we're just using it to heat water so we can have hot showers. That's super interesting. Thanks for sharing. I've definitely learnt a lot. I think we have enough time to dive into wind power as well a little bit. And I think as we were talking before this panel, Viden, you were telling us about how glass is actually used in the construction of wind turbines. Can you tell us a bit about that?
Yeah, sure. It's a bit of a little known fact that, you know, glass is used quite extensively in wind turbines, and more specifically, it's used in the form of fiberglass. So if people are unfamiliar with fiberglass, which probably quite a few people are, it's called a composite material. So it's actually made up. It's a one material, but it's made up of two different materials. So, and it's kind of, those two materials kind of combine together to give kind of enhanced properties. So the composite is made of glass fibers, hence the name fiberglass, and a epoxy resin. And an epoxy resin is just a fancy word for saying glue, really. So those two materials are combined together to give you fiberglass. And to be more specific, this is mainly used in the blades of the wind turbines. So there's quite a few reasons for this, mainly because it's quite light compared to the alternatives for how strong it is. So if you made a wind turbine blade out of steel, it would be horrendously heavy. And every time a gust of wind would come through, it probably wouldn't be powerful enough to spin the steel blade. So that's a pretty strong reason to use it there. And it's pretty cheap in comparison. And what it has done, because of how light it is, it's kind of enabled wind turbines to reach enormous sizes. So initially, you know, everyone's probably seen one of those windmills on a farm. They're pretty small, a couple of meters across in diameter, and the blades are maybe, you know, 60 centimeters, less than a meter long. And now, with the use of these new materials like fiberglass, the longest turbine blade that's currently being used is 107 meters long. So that would mean the blades from tip to tip would be over 210 meters wide. So that's pretty significant from the old faithful windmill on a farm. So yeah, it's a pretty terrific material. And you know, people may not know that, you know, they're coming across fiberglass in every day, because usually it's painted over and it just looks like metal. So for example, it's used a lot in aircraft. So if you've been on a plane, there's probably a few components there that are made of fiberglass, and boats. It's a very common material used in boats because of how light it is and how strong it is. And it's also good because it's easy to make in pretty much any shape you want. You just need a mold and a bit of fiberglass and you're away. So yeah.
Sounds like fiberglass is super versatile, and I just wasn't that aware of all its uses. I mean, I've come across them in my day-to-day life, obviously, quite a lot. That's awesome. What a material. Now, we've talked a bit about, obviously, solar and wind, and we've got gone pretty in-depth into those. So thanks heaps, Jed and Viden. Beck, with these different sources, obviously it's good to have variability, but why can't we use renewable sources of energy all the time?
Yeah, it's a bit of a shame, but they're not always available, because they all need certain conditions to be able to generate some electricity. So if you think about it, like the days when, you know, students can't go outside for lunch because it's pouring rain, like that's not a good day to be able to get a lot of solar energy. Or at nighttime, you know, it's dark, the sun's not out. And there are days when the wind's not really blowing much. So it's hard to predict how much energy we're going to be able to get out of it. Mm-hmm. And then even with our hydro stations, to a degree, you know, we need to be able to capture all that water. So we need to wait for it to rain and flow into our reservoirs before we can actually generate. So yeah, unfortunately we can't use it all the time.
Right. Okay. But so this renewable energy obviously will help us get to that low carbon emission future, that low carbon economy, which I think I suppose we all want. So I think then begs the question, if we can't generate renewable energy all the time, can we store it? How do we store renewable energy? Viden, do you have any ideas on that?
Yeah, that's a pretty good question, Kush. You're on fire today. It's kind of a hot topic, the storage of renewable energy, and it's many people consider this to be sort of the final piece of the puzzle in a renewable energy future because, as Beck said, sun doesn't always shine when we want it to, and the wind doesn't always blow when we want it to. So storage of this energy is pretty important, and it's a rapidly evolving space. Probably by the time I tell everyone about it, something else would have come out, a new technology or something like that. But I'll just start off with like an example that most people are probably familiar with, and that's just a little chemical battery. So this can be what's in your phone, or just your little humble AA battery, or something that's in your PlayStation remote or Xbox remote. And yeah, pretty much grid scale batteries. So when they talk about the Tesla big battery or your electric cars, it's not much more complicated than these batteries, but just thousands of them stacked up together. So once you start stacking them all up together, that's when you get something what's called a grid scale battery. So something that can store a significant amount of energy and also deliver that. So how it usually works is, when there's an excess of energy, so when there's a heap of sun shining and a heap of wind blowing, we can use that excess energy to charge these batteries up. And then when we want to use it, so later at night when you're cooking your dinner, or early in the morning when you're boiling the kettle, you can discharge those batteries to power those things. So that's kind of how we see the benefits of those grid scale batteries. But storage really can be much more simple than that. So say if you go outside and you pick up a rock or a brick off the ground, you've stored energy just by picking that up. So, and then if you wanted to discharge that energy, you just drop it. So if you do want to go out and do this, mind your feet, don't drop it on your foot. But yeah, so that's a very simple way of storing energy, is just picking something up and dropping it. And this is kind of how pumped hydro actually works, which is something where we use here at Snowy Hydro. So instead of a brick or a rock, we just use the water. So we pick the water up, put it at a higher place or a higher dam, and then when we want to use the energy, we just let it run back down the hill. And all we do is just put some fancy spinning turbines in the way, which then help us get out electricity from that process. So yeah, and storage can be quite simple, and there actually are systems that literally just pick up a heavy mass during the day and then just drop it at night when we want to use the power, and that's it. But to kind of show you how many forms there are, as I said, there's chemical batteries and there's hydropower, but then we've also got compressed air, we've got thermal storage, we've got hydrogen, which is got to do with splitting water and recombining water, and then you've got spinning mass. So they're all like current technologies that are being used today to varying scales, but I'm sure I'm missing others, and I'm sure, as I said before, there's probably some in development that we've never even heard of yet that we might be using in the future. And kind of how this helps us today is that when you add storage into the grid, it kind of helps more renewables come online, because those renewables can kind of be more utilized. So yeah, we can store more of the power when there's a lot of it, and we can then save that for later use. So that's kind of how storage fits into the picture that we have today.
Awesome. Okay, so there's so many technologies, and I could already hear a few that I know that we use, whether it's here in Australia or over in Europe or America. So there's all these different types of generation. There's all these different types of storage. So it's a pretty complex problem getting put together. Viden, do you think we're going to be able to get to a stage where we can generate all our electricity from renewables and then store it and use it, so all our demands met that way?
I don't see why not. It's going to take a lot of brain power, people with bigger brains than me. But, if it was easy, we would have done it in the first place like this, instead of relying on the fossil fuel generators that we predominantly use today. So, I mean, yeah, it's going to require a bit of smarts and everyone working together, and, everyone at school. Maybe one day you guys will be working on it too.
Yeah, awesome. All right, well, challenge out there. We're all on notice. We're all gonna, I suppose, have a crack at the challenge and the problem. Now, Beck, so obviously you're our market guru here. how do all of these sources of energy and storage sort of fit together with the national electricity market? You mentioned that before. Snowy Hydro buys energy. Personally, I thought we were an energy generator, but we buy renewable energy from wind and solar. I've heard the term firming being used, being thrown around. Can you tell us a bit about how firming works in relation to the energy market we have?
Yeah, for sure. Well, start off, I'll explain sort of what the energy market is. So it's called the National Electricity Market, or the NEM, and it's a wholesale spot market. So kind of what that is, any companies that generate electricity can go to this place, which is all virtual, but you go to this place and they can sell their electricity and somebody can come along and buy it. So it's kind of like, if you went to a farmer's market, and the farmer might be selling some bananas, and so you go there to buy their food kind of thing. So so it's a market like that. So we sell our electricity from our hydro and gas and diesel power stations to companies like Red Energy or Origin Energy, who then can take that electricity and then sell it on to everyday customers and households. So how it all kind of works together is they work out the price based on like supply and demand. So you really want to be generating as much electricity as you're using, because if you're generating more, then you're kind of wasting it, and if you're not generating enough to meet the demand, then some people are going to be left without power, which is not where you want to be. So but they're like kind of what Varden mentioned before, there are times where the demand for electricity goes up. So I guess like if you think about it, in the afternoon, you go home, you might put the aircon on if you're hot or cold, you turn the TV on, you play Xbox, you make some toast, you're like sort of starting to use all these appliances that need electricity. And if you think about it, everyone around Australia is kind of doing that at the same time as you. So sort of the demand for electricity goes up really quickly, and it's sort of like this peak time, kind of like in the afternoon to night, where everybody's like demanding some electricity. So then you need generation companies to be able to supply some more, to be able to meet that and make sure everyone gets the power they need. So but we were talking a lot about renewable energy and saying that it's a bit intermittent and you can't always rely on it to supply everything you need. So I guess even at nighttime, like when it's dark, people are still using electricity, but we don't have the sun and the solar panels anymore. So what we can do instead is we can use some other sources, like gas, diesel, hydro, even batteries as well, like Varden was talking about. We use the energy that they can produce to sort of supplement the renewable energy that we're getting from wind and solar. So that's where the term firming kind of comes in. So it's kind of like firming up the market. It's like making sure that at all times we're going to have the supply of electricity that we need to be able to meet the demand. So and one key thing with all our firming sources is we need them to start quickly. When you turn on your TV, you want it to turn on instantly. Everyone needs that demand quickly. So we need these sources to be able to come on within 5 to maybe 30 minutes so that we can get the electricity out to everyone who needs it.
Yeah, right. Okay, cool. So it's not like, because we know we're sort of forecasting that there's going to be lots of energy use in the evening, that, we'll turn on a few generators a little bit early, just so there's plenty of supply. It literally has to be matched up, the demand at that moment or at those few minutes needs to be matched by the supply. So that's why we need these on-tap generation sources that are able to generate right then and there. And that's basically what it means, like firming up the supply.
Yeah, exactly. Yeah. So to make sure that at any time that you're going to guarantee that you have enough electricity being supplied to everybody. Exactly.
Okay, cool. And ideally in this renewable energy future, most of that's coming from, your wind, solars and your other renewable sources. But then, to make sure we have the energy, we sometimes use the batteries and all those other sources that you talked about. Yeah,
exactly. Just to make sure that, because like we've all said, if the sun's not shining, but we still need to use some electricity, we can make sure, everyone always has the power they need.
Awesome. All right. Thanks heaps for that, Beck. This national electricity market with all its components is it's pretty complex, but it's very, very, very interesting. So obviously you guys are very knowledgeable, have wide experience. Basically, I want to find out a bit more how you developed this. So what led you to a career of engineering? So what got you interested, and then following on from that, what got you interested in working in the renewable energy sector? Jed, I might start with you. Can you tell us a bit about your story to how you got here?
Yeah, absolutely. So I've always really enjoyed looking around myself and trying to figure out how things work, why the world is the way it is, and that sort of thing. When I got to high school, I had a really awesome physics teacher, a bloke by the name of Mr. Larson, and he really fostered that curiosity and that inquisitive thinking. So I went down that physics path, and I really loved that. And I decided I wanted to sort of leave the world a better place than I found it. So I went into a degree of mechanical engineering with the point to always work in renewable energy, as I think that that's a really good way to do interesting work and still help out the world. Growing up in Albury, I was pretty close to Snowy, so I always sort of knew what Snowy was and what it was about. And I did a project on it in Year 9 history as well. So then I decided Snowy was where I wanted to be, where I could do interesting, meaningful work that would help the world, and where I could also get back to that sort of country living that I really like. How about yourself, Beck?
Yeah, so I got into engineering actually because my dad's an engineer, and he got to work on some pretty cool projects. But to be honest, I didn't really know what engineering was when I was growing up. I just remember like we'd be driving around the city and he'd be pointing out all these cool tunnels that he worked on, and I thought, oh, that was kind of cool. You get to work on some interesting stuff. So yeah, so I decided to study it at uni, and I also was quite interested in like maths and science at high school, which really helps. I think it gives you a bit of curiosity about how things work. So I went and studied it at uni, and then towards the end of uni, I was like looking for different areas to work, and the renewable energy sector seemed like a really really cool place to work in, because it's starting to grow. Everyone's getting more interested in it, and there's only going to be more cool projects coming up. And then I saw Snowy Hydro, and it's I really wanted to move out of Sydney, like live somewhere quieter with more outdoor activities, and be able to work in like cool places like this, where you're out in these remote towns working on some really interesting assets, and also feeling like you're sort of making like a positive impact by working with a company that wants to have a positive impact on the environment, and working in renewable energy. So that's how I kind of got into it. But I'll pass you on to Varden. What are your thoughts?
Yeah, so similar to Jed, when I was a young kid, I was always interested in trying to figure out how things worked, and unfortunately, that kind of resulted in a lot of destroyed toys as I kind of ripped them apart, trying to figure out what was going on the inside. But you can't win them all. And then kind of this didn't really go away as I got older, but I did manage to break those toys as I got older, so that was kind of handy. But then combining this with a kind of liking of maths and science kind of naturally led me down the path of studying engineering at university. I kind of just looked at what jobs were out there when I was around the year 8 and 9 mark, and then just kind of, went backwards from there. And what sparked keen interest in the renewable energy space was a trip I did overseas, and just kind of realised that, the world is we're not really treating it with the respect it probably deserves. And, a renewable energy or job in the renewable energy sector kind of just made sense to me at the time. And, there's quite a few problems in the world at the moment, and renewable energy future is kind of a way to deal with some of those problems, such as climate change and whatnot. That's kind of how that led me to here. And I learned about Snowy Hydro actually when I was in year 9. I did a history project on the multiculturalism of Snowy, and I remember thinking back then that, it seems like a kind of cool place to work because I don't mind skiing. And that's kind of what got me to here.
You say you don't mind skiing, but I've seen you on the slopes. You're pretty quick. You're pretty good. So I think you're selling yourself a bit short there. So you touched on it a little bit there, Varden, about what a renewable energy future sort of means to you. Beck and Jed, any thoughts on that?
Yeah, I reckon it's obviously working towards 100% renewable energy, if we can, and also, everybody taking a bit of responsibility to learn about it, or maybe implement your own solar panels on your own roof. I think it's everybody sort of coming together and working towards sort of helping this problem, and making a future where we can just use renewable energy all the time.
For myself, I would say that as Beck sort of mentioned earlier, that generates a lot of work opportunities in rural areas, which I'm quite passionate about, seeing as I've grown up in a rural-ish sort of place. And also, just reducing that fossil fuel usage will hopefully give us a nicer environment that will last for a lot longer, and everyone will be able to enjoy this beautiful planet we live on for much longer.
Awesome. I couldn't resonate more, I think. It's probably the reason why I'm here, other than the fact that I just find it super fascinating working in the energy sector, the power sector, learning about the market and all these different technologies. It's pretty good for a nerd such as myself. But I love the natural environment. I love skiing. I love going outdoors. So renewable energy future just means that all that is I suppose preserved and in a better state going forward. Well, thanks heaps, Beck, Jed, Varden, for all your knowledge and time and insights today. It's been incredibly interesting. I think we've delved a lot deeper into some parts about glass that I had no idea. So, back on the National Science Week topic of glass more than meets the eye, I think we've really gotten an insight into, some really important materials that go into creating these wind and solar turbines. So I hope you've enjoyed, to everyone out there celebrating National Science Week with Snowy Hydro. So thanks heaps again to our panelists. You're absolutely amazing and super, super knowledgeable. And thanks to everyone from around Australia that's joined us. Obviously, this sort of panel wouldn't happen without you. A few other schools that I didn't mention at the start, but I know we have around. Holy Family Catholic Primary, Cairn Coburn Public School, and then obviously a lot of students homeschooling from around the country. So welcome and thank you. I don't know if we have any questions down there that I can see, or maybe I'm not using it correctly, but if that's all we have, we might wrap it up there.
Yeah, thanks everyone for tuning in. Thanks, Kush, for being a brilliant host.
Thank you. All right,
Thanks,
cheers, guys.
Thank you, everyone. That's the end of our National Science Week panel. Thank you to all involved, and especially our schools.